Mm. So, welcome to this live session. We will be taking up the assignment 3 of the previous run so that it can help you to solve the questions of assignment 3 of this run. So, I hope that assignment 2 so problem solving session was useful for you. So I'll start present my screen. Okay. Yeah. So can you just raise your hand? Okay. So we'll go about solving this session now. The problems, some typical problems we will be solving. Um, so let's start with question number 3. So it states that the presence of earth in the case of overhead transmission lines, then we have been given these 4 options. So increases the inductance, then increases the capacitance, decreases the capacitance, both A and B. So the answer will be C, and I will be trying to explain what is basically the earth capacitance, and I mean how it helps in improve. Yeah. So we have these overhead transmission lines, as you know, just like this. So where these are the transmission towers, and these are the transmission lines. So for our convenience, if we just consider this single transmission conductor or wire. um, so I hope you are able to see my screen. Just could you just raise your hand and let me know whether you are able to see my screen? There is a raise hand option. I believe you are able to see the screen. Just could you just raise your hand? Okay, thank you. So we were basically discussing this. Okay, so, yeah, you can lower your hand now. So we'll be going through some of the typical problems of assignment 3 of the previous run. So it will help you to solve the problems of assignment 3 of this run. So the problems are basically the same. I mean, the approach is the same. So maybe the question may be slightly changed, or the values used in the problems may be changed, but the approach remains the same. So let us start with the first question. So so question number 3. So it says that the presence of earth in the case of overhead transmission line, and we have been given the following options: increases the inductance, increases capacitance, decreases capacitance, both A and B. So it will be option B. So sorry for that, I'll change it. So now let me explain what is basically, I mean, how a capacitance increases due to the presence of earth. conductor, and let's say it is positive charge. So these plus charges will be, at the surface of the conductor, and let's say that the ground or the earth surface is at a distance of h from the center of the conductor. Now we know that the ground surface or the earth surface, it is an equipotential surface having a charge of 0. So charge is 0 here. Now so what happens is that the flux lines or the magnetic field lines, it cuts the surface of the earth nearly horizontally. So if orthogonally. So if I try to draw it, so it will be something like this. So now so you can clearly see that this is at some, so this conductor having some charge is at some potential, let's say V1, and ground it is at potential 0 because there is no charge. So this is at V equals to 0, so there will be some potential difference, and this conductor will try to induce some charge inside on the earth surface. So for our convenience, so what we do is that we use the method of images. So as a result, um, we take this negative charge which is present exactly at a distance h below the earth surface. So it's just the mirror image. So this negative charge is just the mirror image of this positive charge, and as a result, the flux lines, as we know that it starts from the positive charge and ends at the negative charge. So it is it like goes like this. So now as a result, so this system or this whole thing would be equivalent to a uh, conductor system of a single phase transmission line. So current would be going through this, and it would be returning, coming back through this. So the capacitance equivalent to that, as we know, the formula would be 2 pi epsilon 0 ln dm by ds, where dm is the self mutual GMD of the system and ds is the cell GMD. So due to the presence or the effect of this earth on the conductor carrying the current, this additional capacitance or earth, I should represent it by Ce. So this is an additional factor which one has to take into account while calculating the total capacitance of the transmission lines. So this is why if we go back to the question, so it says that the presence of the earth in the case of overhead transmission line, it increases the capacitance. Hence option will be B, sorry, not C. uh, so yeah, so if you have any question, you can speak up, otherwise I will be just going to the next one.
Yeah, you can go ahead.
Okay, thank you. Yeah. Now let us go to question number 4. So I'll be taking up some typical questions. So since this is a 1 hour session, we won't be having sufficient time to solve all the questions, but we'll be taking up some typical questions that will more or less cover the whole 12 problems given in the assignment. Yeah, okay. So question number 4 is pretty simple. So it says that a three-phase overhead transmission line has its conductors horizontally spaced with spacing between adjacent conductors equal to x. So now the conductors of the line are rearranged to the to form an equilateral triangle of side equals to x. Then so as per the question, so this is a system 1 which I have drawn here. So we have three conductors forming the three-phase line, which is spaced horizontally at a distance x. Now this system has been reconfigured to form a equilateral triangle having this kind of spacing, so of x. Now they are saying what would happen to the average capacitance and inductance of the transmission line, of the new transmission line. Now this is very simple. We have to look at the mutual GMD of the system. So wherever the mutual GMD would increase, the what should I say, the inductance of the line will increase because it is directly proportional to the mutual GMD, and where it decreases, the inductance will decrease. So now this is the formula for inductance, as we know. So L equals to 2 into 10 to the power 7 minus 7 ln dm by ds, and whereas on the capacitance, so it is inversely proportional. So from these two formulas you can see that it is inversely proportional to the dm, right? Because and again the cell GMD or DS would be same for both the systems, so it is not, we don't need to care about that. So if I calculate the say mutual GMD of system 1, so let's say we take the first conductor A. So mutual GMD of A with B would be x, and mutual GMD of A with C would be 2x, right? So it's basically the distance of AB then AC for conductor A. For conductor B would be AB BC, and for conductor C would be AC and BC. So it's exactly what I have written here. And since this is GMD, geometric mean distance, so there are 6 terms, so we have to do root over 6. So it comes out to be 2 to the power 1 by 3x. On the other hand, for system 2, it's pretty simple. So they are symmetrical in nature, and it would have a distance. So each conductor is placed at a distance of x. So if we calculate the mutual GMD, it would come out to be x. So therefore, from this we can see that the mutual GMD of system 2 is less than system 1. So as a result, so since inductance is directly proportional to mutual GMD, so and for system 1 mutual GMD is greater than system 2, therefore inductance of system 1 would be greater than system 2. And since the capacitance is inversely proportional, so it would be more for system 2 as compared to system 1. So which is coming out to be option. So average capacitance will increase and inductance will decrease. So option number C. Yeah. So this was question number 3. So if you have any doubt, you can speak up, or otherwise I'll go to the next
Yeah,
question.
it is clear. You can continue.
Okay. 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 So this is question number 2. Or let's solve question number 1. Where was question number 1? So it is mentioned key which of the following are advantages of using bundled conductors. So bundle conductors. So for this, let me again use this. So we have seen key the these are, as we know that these are the transmission towers and these are the transmission lines on the transmission towers, right? So for transmission lines which have a capacity of greater than 220 kV, generally the transmission lines of each phase are represented by a single transmission line. But whenever the capacity increases more than 220 kV, generally what is done, a group of conductors. So let's say I'm using these 4 conductors. So they represent a single phase. So what is being done, they are tightened together with the help of this kind of arrangement. So this is what you call bundling of conductors. So this kind of arrangement is called spacer. So this helps to keep the all the 4 conductors of a phase I mean very close to each other. If this is not used, then this type of system is may be prone to cyclone or high wind speed, which may affect this. So that is why this kind of spacer are used. So we have different kind of arrangement for this spacer. So this is one, then this may be one. So here four wiring arrangements are there. So here three are there, and again this kind of arrangement is also there. So where there are two, I mean it has a capacity of holding two wires. Now, so this is basically bundling of conductors. So now if we calculate the inductance of this 1 and 2, so let's say this is one conductor, and this is the same conductor where there are these four subconductors. So if we calculate the the inductance of this, it would, so the formula is uh, the mutual GMD by cell GMD. So we are not concerned about the mutual GMD because we don't know, or we are not taking care of what are the other conductors that are present nearby these conductors. But if we look at the self GMD, so for this conductor it would be basically this 0.7788 r, I mean the uh, uh, it is the cell GMD of this single conductor. But if we look at this conductor where there are several subconductors which may be at a distance, let's say d from each other, the cell GMD won't be this, it would be uh, you know uh, so the cell GMD, what would happen is it would increase. You may calculate, because if let's say, so it is very easy to calculate. So let's say this is the arrangement, and each of this is spaced at a distance d. So the cell GMD. So it would happen that for the second arrangement, the cell GMD would come out to be greater than the cell GMD of the first one. So as a result, what would happen is that the L2 would be less than L1. So as a result, from this, what we can see is that the line inductance for this kind of system, it increases, it decreases. So as a result, the voltage drop, which would be Iz, it would decrease. So the sending end and the receiving end voltage of the transmission line would nearly be the same. Now this answers our first part, so reduce reactance. Now if we go to the surge impedance part, so surge impedance, as we know that it is root over L by C, right? So as we saw that L, so since this is increasing, this term is increasing, so the line inductance would decrease. So this would decrease. On the other hand, as we saw just a bit earlier that, sorry, uh, this would be right. So this is so if this term increases, the denominator would decrease, which would result in increase of the capacitance. So C2 would be greater than C1. So as a result, the denominator would increase, and as a result, the surge impedance would decrease. So this you know makes us know that the surge impedance reduces. Now voltage gradient, basically in a transmission line, so if you know that the L, what we calculate, its unit is given in millihenry per kilometer, or the capacitance is microfarad per kilometer. So this changes. So from this we can easily see that the L or the C, it increases, I mean it changes with the length of the line. So there is a voltage gradient. Now um from this, so if the L decreases, so it would reduce the inductance of the line, right? And as a result, the voltage gradient would decrease. So in a nutshell, bundle conductors help to reduce the XL and XC, so which reduces the net this Z, and as a result it reduces the voltage gradient. So as a result, the it would option number 2 would also be the correct option. So the answer is D, all of the above. So this was also a pretty simple kind of a question. I hope this was clear. Yeah, if this is clear, now let us go about solving question number 9, which is, now these are all kind of numerical questions. Yeah, so I have tried to solve this beside the just beside the question only. So what it is saying, calculate the capacitance to ground. So just see this line, ground. So the thing which we just saw earlier, considering the effect of earth in the case of a single phase line whose conductors with diameter of 1 centimeter are separated by 2 meter and which are lying 10 meter above the ground. So the line length is 60 kilometer. So in this type of questions, a good thing would be to draw the circuit. So yeah, the approach to the problem would be simpler. So there it is being said ki a single phase line. So single phase line means there would be two conductors. So one for carrying the current, one for the going path and one for the returning path, which is highlighted by A and V. So it is told that we have to calculate the capacitance to ground, and if this is the surface at a distance of 10 meters, so we have to also consider the effect of earth. So there will be a kind of fictitious conductor at a distance of 10 meter below the earth surface, so which is also represents this both this conductor A and B. Now this would be the approach to solve this problem. So there is a direct formula first of all. So this capacitance line to ground is represented by 2 pi epsilon 0 this ln d by r into daa dash divided by dab dash. So daa dash is 20 meter and dab dash is just this Pythagoras theorem 20 square plus 2 square. But instead of using this formula, you can also calculate this the capacitance of this system just by, so if you just remove this surface and just consider that this is a simple uh, a bundle system where this is this AA dash represents one line and this BB dash represents another line. So this is just a bundle system of single phase transmission line. So first we need to calculate the cell GMD of AA dash, which would be just this, so it would be very simple. So 20 meters into the radius of this conductor, which is 0.5 centimeter. We would be getting this. So this would form the cell GMD of the system. Now we have to calculate the mutual GMD of the system, which would be the distance between A and B and A, B dash. So you would get the mutual GMD of the system again, and later put into this formula. So this formula. So there would also be a 2 here. Sorry. So just this formula, and you would get this kind of answer. So it won't be exactly 9.829. I think it should be around 9.3 or 9.32. I did that. Now this is the capacitance. So this is the unit in farad per meter, right? So if I multiply it by 60 and also, so there will be also a 10 to the power 3 here. So since this is 60 kilometers, so now if you convert it into microfarad, it would be coming out to be 0.5573 microfarad, which is our option C. So this is a pretty simple problem. You just have to draw this kind of diagram, and the approach would be the same as for other kind of systems for bundled conductors of single phase transmission line. So you would be getting option C only. I hope this was
Yes, yes, it is clear. Yes.
okay. Now let us go to this problem. So these problems are pretty simple provided that you have gone through the previous assignment. So the approach is just the same, just that the calculation of capacitance, the formula is just the different. But for this type of transmission line problem, we just have to calculate the cell GMD and mutual GMD. We just have to know how to calculate it. That's it. You just have to fit into the formula and you will get the answer. So 1 minute. Yeah, I'm just making sure that the recording is on because I have to submit it. Okay. So 220 kV 3-phase 50 hertz fully transposed line of length 200 kilometer has a bundling arrangement. Again, this word bundling is there, of two conductors per phase as shown in figure 3. So since there are three phase line and it is written that two conductors per phase, so per phase there will be two conductors which would represent one phase, right? So this is a dash, so there are two conductors which would represent phase A, phase B would represent these two, and phase 3 would represent these two conductors. So the phase current is equally shared by the two parallel conductors. So I mean this is a parallel connection, so that is why parallelly shared. So it is being told that determine the total reactive power in megawatt supplied by the line charging capacitance. So this is pretty simple. So I have written here DAB. Now one thing here I would like to mention is that so while calculating the mutual GMD of this system, you don't have to take into account of this extra zero point 0.5 meter, because you see that the spacing 15 meter is far greater than this zero point 0.5 meter. I mean, you can be accurate. Let's say you calculate the distance of this A, conductor A to conductor B. So what? So again, it would be 15 meters only. But let's say if you calculate the distance of A and B, so A, B dash, so it won't be 15, right? It would be what, 15.5 meter. But you see that this 15, I mean, if you calculate and get the final answer, the approach of this, so if I neglect this zero point 0.5 meter while calculating the mutual GMD, it would be the very close to each other. So I mean time would be saved while solving the problem. So now if we calculate the cell GMD of A dash, it is this very simple. So distance of A from A dash is 0.5 meter, and distance of A dash from A is again 0.5 meter, and the radius of each conductor is 1.5 centimeter. So I have just put it here. So it comes out to be 0.0866 meter. Again, which is the cell GMD of B dash also and C dash also. So as a result, we can say that the system cell GMD or DS is 0.0866 meter. Now, the mutual GMD of AA dash would be the distance between this and this, which is 15 meter, right? So, just for convention, I've written it as DAB. And from this phase, first phase from third phase would be 30 meters. So, you just do it 15 into 30 whole root, it would come as 21.213 meter. Now, it is exactly the same as this because this and this are placed at a same distance from each other, so I haven't calculated it. So it is exactly the mutual GMD of C dash. Now
I have a question here.
yeah.
In case of this mutual GMD of A dash,
Hmm.
um, we would go by this method, right? AB, distance between AB and AB dash, and AC dash. Similarly, A dash B dash, AC dash, right? But we
Mutual
have
GMD
considered
you're
only.
talking about, right?
Yeah, yes.
Yeah, that is what I told now. See, A B dash, what would be the distance? It would be 15.5 meter, right? And
Okay,
A B would be what? 15 meter. And the distance between A dash and B would be what? 15 minus zero point 0.5
point
meter,
5.
right?
Yes.
So, but if you calculate that, the mutual GMD would be really very close to it, which won't
Okay,
affect
okay,
your calculation. So at the
okay, okay.
end, when you calculate the capacitance, So it would be really very close. So just for
Okay, the
your
result is not
convenience,
going to make a big difference. Yeah.
no,
Okay.
no, 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 not at all, not at all. So it
Okay.
would just save your time. So suppose you are preparing for GATE exam also, this kind of question comes. So you have to quickly solve this problem. In that scenario, this kind of approach would help.
Okay.
Yeah.
Okay.
So mutual GMD of B dash would be distance of this phase, second phase from the first phase, which is 15, and this is also 15. So you get it as 15. Now mutual GMD of the system would be cube root of this, all these three mutual GMDs, which come out to be 18.897. Now, okay. So for calculating the total reactive power, we have to calculate the line capacitance. So line to neutral capacitance, mind you, not the line to line capacitance, because we, I mean, we have to take the. So I mean, the convention is that we have to calculate the line to neutral capacitance. So that is why this two term would be coming. Otherwise, this would be plain pi epsilon 0. Now the line voltage here, it was mentioned 220 kV. So while calculating, I mean, this is per phase reactive part. Okay. So the pretty simple V square by R. So you could do this. Just replace XC with this thing, and you just finally the reactive power is 3 times this per phase reactive power, which comes out to be 31.384 megawatt, which is option B. So this is also a pretty simple question. I hope this is clear.
Yes, it is clear. I just have one more question, everyone.
Hmm.
Here, the question is given for 200 kilometers transposed line. So how it
Yeah.
is going to affect if it is untransposed line, or what kind of formulas we will use it for untransposed line, if it is 200 kilometers untransposed line?
See, transposed line basically means that. So let me use this. See, first of all, let me say that since this kind of arrangement is given, you just have to follow this convention. So untransposed line means that there is this phase. So let me represent it by R, Y, and B. Okay, so this is untransposed line. But in case of transposed line, what happens is that, so if this is the sending end and receiving end, so transposed line, basically in transposed system, the position of the conductor changes. Okay, so let's say these are phase R, Y, and B. Now after a certain distance, phase R would occupy the middle position and finally the bottom position. Now phase B would go to the top and then go to the middle again, and phase Y would. So this kind of arrangement is there. So if I draw this R, again B, Y, and then BY. So this is the concept of a, so this is untransposed, receiving end and sending end. This is untransposed and this is transposed. So see, basically the approach is the same. Now when in the question, so in this question it is being said that there is this fully transposed line. So by default you would assume that the conductors A, B, C would occupy this kind of position. But for that you don't have to, do any changes in this question. It is just the same. Only if you, when they say that there is this untransposed line, it would mean that the position of the conductors won't change, and you don't have to do anything extra while solving the problem. That's it.
But for both the types, let's consider the question is given as transposed or untransposed.
Yeah.
If the calculation method is going to be the same, then result is also going to be the same thing. Then how the value of
No, no, no,
capacitance
no,
or
no.
inter
See.
yes.
For transposed and untransposed line, what happens is that, so let me explain again. So for untransposed line, what happens? So let's say the sending end voltage is 10 kV, 10 kV, and 10 kV. Now what happens is that for untransposed line, so there would be some drop here, right, in each line, IZ in each line. So what happens is that due to this, there would be some voltage drop, and the receiving end voltage would be few magnitude less than the sending end. So let's say this is 8 kV and this is 8 kV. But what happens is that the middle line gets a higher voltage drop. This is because, you know, when there is this the current flowing through this conductor, there would be a magnetic flux linkage with each of this line. But for R phase, there the linkage would only be between R and Y line, and for B also this would be same. So as a result, what happens is that the voltage drop in the middle line would be more. So even though there is no fault, the system would be unbalanced. But in the case of this, there would be equal voltage drop, so each line would be having the same voltage, right? So in this question, they haven't told you anything about what would be the voltage drop in the line, right? So that is why you don't have to consider anything special while calculating the capacitance of the line. So it would be the same, right? It would be the
Okay.
same.
Which means the capacitance and inductance value of the line for both transposed and untransposed line is going to be the same thing.
um
If I consider if this question is untransposed, I'm not considering about the voltages drop here.
yeah yeah yeah
Then
yeah 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 when you are considering the voltage drop, so let's say what would be the voltage drop in the sending end for untransposed and transposed line, then there would be some difference. Okay, so first of all, no, the voltage, the inductance of this phase B would be more than phase A and phase C, right, for untransposed line.
okay, in case of untransposed line, then I need to split this 200 kilometers into 3 halves. If
Yeah,
then I need to do the
but that
calculation.
kind of question would become more complex. Okay, so those kind
Okay.
of questions you won't get
Okay.
specifically. That would be a more, because in that case you have to, you know, get the distance, so where this where the position of this line is being changed. You have to know that, then you have to calculate the inductance till that point. Then from that, so let's say this is being, so let's say this is a 300-kilometer line. So you have to split it at, let's say, 100, 100, and 100. You have to calculate the inductance till this point, then from here to here again, then from here to here again. So that would be a more complex problem. So this kind of problem you won't get in the UG level or in GATE.
Okay.
Yeah. Okay. So now this is again another problem. So this is also a pretty simple problem. So it is being said that a three-phase 220 kV 50 hertz transmission line has flat horizontal configuration of spacing of 8 meter between the adjacent conductors. So here I have drawn here. So this is a very simple kind of arrangement. You this line very carefully. So the conductors are numbered to hard drawn. So there are different type of conductors, right? So this is one of one class. So the what you need to look at is that the effective outside diameter of the conductor is 1.6 kilometer, which gives us the radius. Now again, charging current per kilometer of the line. So again this same thing. So we have cell GMD of the line, which is again, so since this is not a bundle system, only one conductor per phase, so the cell GMD would be very simple, 0.8 into 10 to the power minus 2 meter. Now mutual GMD of the line, as we saw in one of the question, so the approach is the same. We have to calculate the distance between A and B, then A and C, which is 8 into 16, then A and B, B and C, which is 8 into 8, and then C and A and C and B, which is sorry, C and B and C and A, which is 8 into 16. If you calculate, it comes out to be 10.079 meter. Then fit in this formula again, the line to neutral capacitance. So 2 pi epsilon 0 ln dm by ds, which comes out to be this. Again, your line voltage is 220 kV, so the charging current is very same. I'm charging current per phase actually. So this is very simple formula. You just place all the things and you get it as so just mind, I mean, keep note of the unit. Okay, so this is farad per meter. They have told you to find in milliampere per kilometer, right? So you have to do the necessary changes. So sorry, there is a mistake. So this will be milliampere per kilometer. So just do that, and this is very simple. So this is option B. Very simple problem. I hope this is clear.
Yes.
Yeah. Now this is an exercise I have left for you. So this is also very simple. So this is again, you see fully transposed double circuit line. Yeah, see. So answering to your question, so just see the arrangement of this kind of conductor. This is a three-phase transposed double transposed sorry, transposed double circuit transmission line. So just see the positioning of this type of conductor. So it is not like this kind of thing. So you know, this and this and this and this and this and this. So this is phase A, this is phase B, this is phase C. This is a transpose line. So that is why phase A and phase A dash are at a I mean, they are not, if you see, the conductors are not the distance between this C and C dash is not 2 meter, or what I can say, this is not this kind of arrangement. So this is what transposition means, right? You are placing different conductors at different length. So for this problem, you just have to calculate the cell GMD and mutual GMD. So cell GMD for, so you have to calculate separately for A and A dash, then B and B dash. And if you see that C and C dash, the cell GMD would be same as A and A dash, right? So cell GMD of A and A dash would be the distance between A and A dash would be 6 square plus 4 square, and you also have the radius, so you can calculate it for each of these. And again, after calculating the cell GMD, you have to look out for mutual GMD. So mutual GMD would be distance between AB, then AC, then AC dash, then AB dash. Similarly, BA, BC, BC dash, BA dash, then again CA dash, CA, CB, and CB dash. From that, you get the mutual GMD of the system, cell GMD of the system. You calculate the capacitance. From there, you calculate the reactance, and you get the this charging current, or the what they are saying, this power megawatt. So this is also in the similar, very simple problem. So you can solve this. So yeah, now, so let us come to some simple problems since we have some time. Uh, Now, this is problem number 5. So it is being said that the horizontally placed conductors of a single phase overhead line of a 50-kilometer length operating at 50 hertz are having outside diameter of 1.8 kilometer, and the spacing between these centers of the conductor is 2 meter. So calculate the capacitance between these two. So this is very simple. So you have the radius, you have the distance between these two conductors A and B, which is 2 meter. Now system cell GMD would be this thing only, and mutual GMD is 2 meter. So now, yes, just note one thing. Here it is being said that the capacitance between two conductors, right? It is not asking for the neutral to line capacitance. So that is why there is no two term here. So if there was a neutral to line capacitance, this would have been CAN. That means A to neutral or B to neutral. That is why this two term would come. since this is asking just between these two conductors, so this is pi epsilon 0 ln of gm by gs. You just put it here, and again be careful of the unit. So this was farad per meter, so this is microfarad per kilometer. That is why I am multiplying this 10 to the power minus 12 with 10 to the power 9. So that is why I'm getting 10 to the power minus 3. So you just calculate it here. Yeah, so they are asking for the length, I mean, not per kilometer, microfarad, not per kilometer. So you have to multiply it with 50 and you get 0.257. So this was pretty simple problem. I hope this was clear.
Yes.
Yeah. So now this is also again a very similar problem. So this is again bundling arrangement, and they have asked to calculate the capacitance to neutral. So again this formula would be there. So two term would be there, and again you have to calculate the cell GMD of the system and mutual GMD. So sweet in this formula and you get the thing. Yeah, so this is also a simple problem. So it is saying ki a three-phase 50 hertz fully transposed line has two conductors of 2 centimeter diameter placed at the corners of a three triangle. Which now see the distance which side 5 meter, 6 meter, and 7 meter respectively. So here I have drawn this kind of arrangement. So it is not an equilateral triangle. Therefore, they have asked to calculate the capacitance to neutral per kilometer per phase. No, yeah. So again, the cell GMD would be the radius of the conductor only to 10 to the power minus 2 meter, and the mutual GMD would be the geometric mean of the distance between these two. So 6 into 5 into 7, which would be this thing, 5.994. You fit into this formula, you get the answer, which is your option B. So this was also a similar problem. Now, yeah, this is also a very simple problem. So calculate the 50 hertz capacitance. So capacitive susceptance, so which is inverse to reactance, right? That is why this is mho. So inverse of ohm to neutral per kilometer of a three-phase double circuit line with transposition as shown in figure 2. Yeah. So the spacing between all of this system is given. So D7 and R is given. So again, cell GMD would be what? Radius of this conductor and the distance between these A and A dash, right? So this is R square into DAA dash into DA dash A. Which is equal to the cell GMD of each of these subconductors B, B dash and C, C dash. So you calculate it and get the value. So here I have written every distance. So A, C dash would be 5D and so on. Now mutual GMD of A dash would be distance between AB, then AC, A dash C, A dash B, A dash B dash, and A dash C dash. So exactly this is what I have written here, and if you place these values, you will be getting a value of 13.2 meter, which is again this is equivalent to mutual GMD of C C dash, because this is exactly equivalent to A dash in terms of the positioning. You can calculate for yourself and just check. This I have not done. Now mutual GMD of B B dash would be again this distance AB BC, then BA dash, BC dash, right? Then AB dash, BC dash, B dash A, B dash C dash. You calculate it and it comes out to be 11.7. Now mutual GMD of the system is the cube root of mutual GMD of each of these conductors, phase, sorry. It comes out to be 12.706 meters. Now capacitance to neutral so it is this again the same formula, and capacitive susceptance is basically inverse of this. So 1 by, so capacitive reactance would have been 1 by 2 pi f into the capacitance. So it is just the reciprocal of that. So directly 2 pi f into this thing. So it comes out to be 5.5261 micromho per kilometer. So which is option number C. This was again a pretty simple problem. I hope it was clear. Yeah. Yeah. All the problems have been solved. So I would be providing the link to this video and also this material along with the question. You just go through it. I hope this will help you in solving the assignment questions. And yeah, so if you have any other doubt, you can ask. So the session is more or less over since we have solved every question here.
That is clear. I don't have any doubts. Clear.
Okay.
Looks to be the
Okay.
same like the inductance part.
Yeah,
what we
yeah,
have
yeah,
seen in
yeah,
the previous
exactly
session.
the same. Yeah. Okay. So we will meet again next week with assignment number 4. So if you don't have any questions, you can leave the meeting. The session is over.
Okay.
Thank you.
Okay. Thank you.
Thank you.